Up. It's exactly time. You guys have any questions before we get started, Sam and Michael?
No, sir.
All right. Well, we're going to jump right in. I decided to go ahead and spend a little bit more time on those last examples from chapter three. So we're going to do that now, and then we'll move on into chapter four as well, because we don't have enough problems left in chapter three to just stop after that. So we'll go ahead and get started. I want to remind you guys, I told you this the other day, but I want to make sure everybody knows, so I'm putting it on the video again. I am going to change your online test dates, and the dates will be changed on the syllabus, but just the online test dates. And the reason being is that my intent is to give you an online test every two chapters. But if I only fit one online test in between now and your face-to-face test, that means then your face-to-face test will only be on the next two chapters, and I definitely need your next face-to-face test to be on more than chapters one, two, three, and four. So I'm going to try to fit in another one in there. And during the summer, it's very frequent that we have literally a face-to-face, I mean, an online test every week. Uh, and usually we try to shoot for the face-to-face tests every 2 or 3 weeks. So that's what's going to happen. As soon as it's done, I'll post an announcement, and that announcement, as far as I can tell, is supposed to be sent to you guys via email, and you'll see it in the change in the syllabus as well. So just keep an eye on that. It's probably going to be, since I like to give you guys a week notice, so it's probably going to be done tonight, and you'll have an online test that'll be due Wednesday. And the same thing for my other class. They're probably going to have the same thing happen to them on Wednesday as well. So, anyways, anybody have any questions before I get started? I already talked to Sam and Michael about it, but Nathan, do you have a question? All right, let me go ahead and all good. Thank you. I'm going to go ahead and share my screen with you guys, and we're starting off with a conceptual example 410. It says a hockey puck is sliding at constant velocity across a flat horizontal ice surface that is assumed to be frictionless. Which of the sketches in figure 420 is the correct free body diagram for this puck? What would your answer be if the puck slowed down? So that's the conceptual example 410. I've read it to you. I may read it again, but you guys can definitely read it as well. Now I'm going to go ahead and share my screen with you on my iPad. So let's do that, and hopefully that will go very smoothly. We'll find out in a second if it does. Yep, it does. Woohoo! I've taken the time to prep a little bit, so I already have the necessary stuff up about this problem. So you see conceptual example 410, it says a hockey puck slides on a frictionless surface. A, which is the correct FBD, free body diagram? And then B, what if the puck is slowing down? So this is a common misunderstanding. And in fact, if you think that this free body diagram right here is the correct one, then that's you exemplifying what I told you guys about, where inevitably my students will turn out to be very Aristotelian. Their ideas of physics are very consistent with the ideas of Aristotle. That's why Aristotle reached those conclusions, because it's so obvious when you see it that clearly in order to keep something moving there has to be a force pushing forward. But if that's the case, then what actually would be supplying that force F that's making it move forward? We know we have to have a normal force. I explained that using Newton's first law and Newton's second law. We know it has a weight, and of course your book calls that F sub g. I generally call it W, so that's where I wrote W equals Fg. And notice that's common to each of the three free body diagrams. This one is suggesting that some force is making the object move across the frictionless surface, and the fact that you have no way of pointing to what actually is applying that force tells you that force doesn't exist. In reality, when we're taking physics 241, in other words, we haven't gone to 242 where we cover electric fields and magnetic fields, and sometimes you cover the strong nuclear force and the weak nuclear force. In those areas, there's only forces that are a result of physical objects touching it, except for gravity. Okay. Gravity is the one thing that acts at a distance in physics 241. And what the weight is gravity pulling down on this puck. And it's literally the earth pulling down on the puck. And in fact, the action reaction pair counterpart to that would be the puck pulling up on the earth with exactly the same force, only the force is in the upward direction instead of the downward direction. So this diagram is not it because it's frictionless. It's moving at a constant velocity across the surface because it's frictionless. This one would suggest that maybe something's slowing it down, and that would be more consistent with there being a friction force. So that can't be the answer to A. So in fact, this middle diagram is the answer to A. So with that in mind, I'm going to go ahead and write, oops, there we go. With that in mind, I'm going to go ahead and say that's the answer for part A. Okay. Now, what if the puck is slowing down? If the puck is slowing down, that means there's some force that's causing it to accelerate. Remember, acceleration can mean speeding up, slowing down, or we'll learn later, it can also mean just changing direction. Okay. Any one of those or any combination of those would actually be consistent with acceleration. So if you're speeding up, that's acceleration. If you're slowing down, that's acceleration. If you're changing direction, that's acceleration. If you're speeding up and changing direction, that's acceleration. If you're slowing down and changing direction, that's acceleration as well. So this is the answer for part B. Hopefully that seems reasonable to everybody. Anybody have any questions on that? Okay, the free body diagram is a very, very important. Thank you, Michael. It's a very, very important concept. You've got to be able to get that right. And not only that, this chapter shows you some very specific things about doing those free body diagrams. So it's really this chapter and the next one are the two probably most important chapters regarding dynamics. Just like chapter three was probably the most important chapter involving kinematics, and it's also the most important chapter considering vectors. So let's move on to example 411. Of course, always would want to go in and read the author's example and see how they explain it. But the main thing is make sure you understand every one of these examples. You should be able to regurgitate them at the drop of a hat. In other words, with the book completely closed, you should be able to solve them. Or maybe with the book closed, except for just the statement of the problem, say like this right here. If you just look at this much of problem four, oh, I'm telling you to look at problem 411, and I'm not sharing the screen with you, so that's not very helpful. I apologize for that. But if you could just read the question and look at the diagram that comes with the question, if you can answer it from there, then you've understood the example well enough. If you can't do that, you're not quite understanding the example well enough. So remember that with every example. And it's very rare that I would say one example in a chapter is not required for you to know. So I would just go on the assumption that virtually every example in the chapter has to be understood. When I get to subsections that have an asterisk by it, sometimes I omit those sections, in which case those examples are not going to be tested, but they might appear on homeworks and practice tests. So just keep that in mind. So now example 411, pulling the mystery box. So we're going back to that 10 kilogram box that we talked about in example 4.2, I think it was, but it said, and later in 4.6, it says, suppose a friend asks to examine the 10 kilogram box you were given. Notice, by the way, just this is not related to physics, but notice how you put a dash between the 0 and the kilograms when you say examine the 10 kilogram box. When you're using the 10 kilograms as a descriptor, you should separate the number from the unit with a dash. If you're just saying a box weighs 10 kilograms and it's just supposed to be 10.0 space kilograms, that's why that appears in there. So hopefully that's just something that'll help you going forward with basic grammar and mechanics of writing. But anyways, suppose a friend asked to examine the 10.0 kilogram box you were given, example 4.6, figure 415, hoping to guess what is inside. And you respond, sure, pull the box over to you. She then pulls the box by the attached cord as shown in figure 421A, which is exactly the figure that I have drawn on the left here on my iPad. along the smooth sur or, excuse me, she then pulls the box by the attached cord as shown in figure 421A along the smooth surface of the table. The magnitude of the force exerted by the person is Fp equals 40.0 newtons and is exerted at 30.0 degree angle as shown. Calculate A, the acceleration of the box, and B, the magnitude of the upward force, Fn, exerted by the table on the box. Assume that friction can be neglected. So this is a little bit like that previous one where I had the person pulling up on the box, I had the person pushing down on the box, and I also had the person with no additional force acting on it. In all three cases, I had to calculate the normal force. Same thing happens here. To calculate the normal force, you're going to have to use Newton's second law in the y direction because y I've chosen to be perpendicular to the horizontal surface and therefore it'd be in that direction. So let's go ahead and start. I've taken the time to go ahead and draw the free body diagram in addition to the picture. So that's the free body diagram. Notice I do take the time to write negative vectors, vectors that actually point in the negative x or the negative y direction. I'll draw those as red, or I'll try to most of the time. And positive vectors, vectors that point in the positive y direction or the positive x direction, I'll try to draw those as either blue or green to make it more like, stoplights or whatever like that. But sometimes they even uh, sometimes I even use blue for whatever reason. And then any vector that's not parallel to an x or y axis, I usually just use the color that I'm writing the question with. So in this case, you see that I've written the FP vector in the color purple. And that just is a reminder that, hey, this vector can't be used. That 40 newtons is not going to be used directly. I have to alter that 40 newtons before I can use it. So to alter that 40 newtons, I have to compute basically the components of FP before I can do anything. So that's what I'm going to do. What I want to remind you to do is whenever you're trying to break a vector up into its components, imagine traveling from the tail of the vector to the head of the vector, from the tail to the head, which would normally be like that. But what I want you to do is imagine going from the tail of the vector to the head by only going parallel to axes. So that means you could either go a lot parallel to the x-axis first and then parallel to the y-axis, or you could go parallel to the y-axis first and then parallel to the x-axis. It doesn't matter which one you choose, you'll get the same answer either way, but that's the way we figure out whether the x component is positive or negative and whether the y component is positive or negative. So if I choose to do the x direction first and then the y direction, then this is what I will get. So the x direction, when I go to the right, that's clearly the positive x direction. So that's FP sub x. And then when I go in the y direction, I got to go up, and that's also clearly in the positive direction. So I'm going to make that one green as well, and that's FP sub y. So we can use our trig functions. And remember, until you get up to speed where you can do this instantly, you want to go ahead and every time just go ahead and write down what cosine is and write down what sine is and then solve it for the appropriate component. As you get better and more experienced, you can consider skipping steps and just jumping right into the x components or whatever. So what I'm going to write is the cosine of, and actually I should probably stick this back in purple. I'm going to write the cosine of 30.0 degrees is equal to adjacent over hypotenuse. Remember, the adjacent is the side that's touching the angle. The hypotenuse is the side that the right angle mark acts like an arrow pointing to. So if, for instance, if we imagine the right angle mark being this, that looks like an arrow that points to this vector, which is the hypotenuse. And then the opposite side is the side that's not touching the triangle, or excuse me, the angle. So now adjacent over hypotenuse gives me FP sub x divided by the magnitude, which is 40.0 newtons. And we see that FP sub x is going to be positive, so I'm going to say FP sub x is equal to positive 40.0 newtons times the cosine of 30.0 degrees. And that should give me, I think it's 34.6, but let's see. 40 times cosine 30 is equal to, yes, 34.64. So that's carrying one extra digit beyond the sig figs. That's good. Now I'm going to do sine of 30.0 degrees. Sine is equal to opposite over hypotenuse. Remember, either so, ka, toa, or some old horse came a hopping through our alley. In this case, it's the opposite, which is FP sub y, over the hypotenuse, which is 40.0 newtons, and we see that it's positive. So what that means, and I didn't need to write the equals there, what that means is Fp sub y is equal to positive 40.0 newtons times the sine of 30.0 degrees. And of course, the sine of 30 is 1/2. So that gives you 20.00 newtons positive as the x component. Now that I have all of my vectors rendered in x and y component forms, remember the normal force only had a y component and the weight only had a y component. So I don't have to write that. I know that the x component of the normal force is 0. I know that the x component of the weight is 0. So I don't have to write those. Even if I had to add the vectors, I just know automatically that the components are 0. In this case, what we have to do is now apply Newton's second law of motion for motion in the vertical direction. Now, what we're predicting here is this person is going to pull this box like this, and the box is just going to slide horizontally across the table. That means the y coordinate's not going to change at all. Since it's not changing at all, that means the displacement in the y direction is 0, and therefore the velocity in the y direction is 0, and therefore the acceleration in the y direction must be 0, because the velocity won't necessarily in the y direction is going to be 0, but it's always going to be 0, and that's what makes the acceleration 0. So now I can go ahead and write the summation of the forces in the y direction equals mass times acceleration in the y direction. But as I just argued, the y direction acceleration is going to be 0. Because of that, I can go ahead and say the normal force, which is Fn, is positive. And remember, the left side of Newton's second law is always a sum of forces. So I add and add and add, but some of the forces will have a negative magnitude for that component. So instead of writing plus a negative, I usually just write minus. So keep that in mind. Uh, Fp sub y is another positive component. So that's 20 newtons. And then we have W, which points in the negative direction, so that's minus 98.0 newtons, and all of that is equal to 0. Therefore, we can now figure out that the normal force is actually equal to 98.0 newtons minus 20.0, minus 20.0 newtons. So Fn is in fact equal to 78.0 newtons. And again, I just added an extra digit there just in case we needed it for a subsequent calculation. So I now have part B, which I wasn't really shooting to solve part B, but that's what I solved first, and that's just fine. Okay. Now I'm going to jump to part A, and in order to do that, I need the summation of the forces in the x direction equals mass times acceleration in the x direction. But in this case, the x direction is really the only acceleration, so I need not subscript that. I can just call it A, and that's what I'm going to do. I'm just going to call it A and not worry about subscripting it. In this case, you'll see there's not many forces acting at all. In fact, there's only Fp sub x, and Fp sub x is 34.64. So I'm going to say 34.64 newtons is equal to the mass, which is 10.0 kilograms, times the acceleration a, and that's it. We don't have to subscript the a, like I said. So we can go ahead and solve for a, and what we get is a is equal to 34.64 newtons divided by 10.0 kilograms, and therefore the acceleration is 3.464. And remember, a newton is a kilogram meter per second squared. So when we divide by a kilogram, all we have left is meter per second, like that. And that's our acceleration. Any questions on that? And if you look at the book, you'll find out that that's exactly the answers they got. They got an acceleration of 3.46 meters per second every second. And remember that just because we're in chapter three, that doesn't mean the kinematics go away. It would be very normal for me to say, take this as an example, and then say part C. Uh, if the box started from rest, how fast would it be going after 2 seconds? How fast would it be going after 3 seconds? And part D, I'd say if the box started from rest, how far would it have traveled in 1 second? How far would it have traveled in 2 seconds? Or how far would it have traveled in 3 seconds? All those kinematic questions are still something that you have to be aware of and be ready to do. By the way, if we wanted to know how fast it would be going after 1 second, well, this is telling us that the velocity is going to change by 3.46 meters per second every second. So after 1 second, it's going to go from 0 to 3.46 meters per second. After 2 seconds, it's going to go from 0 to twice 3.46, which would be 6.91. So that's how fast it would be going after 1 second and 2 seconds. If I wanted to figure out how far it would go, then I have to use 1/2 AT squared plus V0T plus Y0 or X0 in this case. And the Y0 is 0 and the V0 is 0 because it started from rest. So the distance it would travel after 1 second would be 1/2 of 3.46. That would be 1.73. So 1.73 times 1 second squared would give me 1.73 meters. And after 2 seconds, it'd be 4 times as big as that. So I'd then multiply 1 point, what did I say? 1 point, it was 1.5, 1.76. So it's going to be 4 times 1.76, which is the same thing as 2 times 3.46. So that'd be 6.91 meters is how far it would travel after 2 seconds. So that's just me doing it off the top of my head. I don't expect you to be able to necessarily do it off the top of your head, but I do expect you to realize that I'm using the equation V equals V0 plus AT, or I'm just using the idea of what this acceleration means. And that's why I keep telling you to say the acceleration is 3.46 meters per second each second because you can then automatically fill in the answer, especially if it started at 0. Additionally, when I ask you for the distance traveled, you should be thinking, oh, x equals 1/2 AT squared plus V0 x times t plus x0. And in this case, it started from rest, so V0 is 0. You can always set x0 to 0, and therefore we just get 1/2 AT squared, which is where I got the 1.76 for the acceleration because it's 1/2 times 3.46, and that gives us 1.76, and then times t squared after 1 second. T is 1 times 1, so that would be just 1 times 1 times 1.76. Any questions on that? I probably sound like a meth addict saying that so fast. I'm sorry. Uh, I wasn't trying to talk that fast. I was just trying to get the idea across. All right, so we've done example 411. Let's move on to example 42. 412. Actually, I have another example that I like doing instead, but it's sort of like example 412. So I'm going to say just plain example. So let's imagine we have a box and another box and a third box like that. This is M3, this is M2, and this is M1, and they're connected to each other via a rope, and they're lying on a nearly frictionless surface. And I'm imagining pulling this with a force FP is equal to, let's say, 100.0 newtons. Okay. I'm going to say that M1 is equal to 15.0 kilograms. M2 is equal to 20.0 kilograms. And M3 is equal to 10.0 kilograms. And what I want to know is A, the acceleration. So I want to know the acceleration of this chain of boxes. For part B, I would like to know the tension T3, which is the tension on the rope pulling three. So T3 is equal to question mark. Part C, I'd like to know tension T2, and that's it. Okay, so that's what I want to know from this problem. Now, this is a good example. It's a little bit bigger than example 412. 412 does the same thing as what I'm trying to do here, except 412 only has two boxes. And I wanted you to see what happens not only with two boxes, but with three boxes, because that allows me to make one box heavy and then the next box a little heavier and then the next box lighter. So I could actually have some variance and you'd see some stuff. So what we have to do to this is a couple different ways we can solve it. For one thing, Newton's second law does apply to a system. Like I could apply Newton's second law to this train of boxes, if you will. Or I could apply Newton's second law to each box individually. If I applied Newton's second law to each box individually, then that would allow me to determine what the tension T3 is and what the tension T2 is. But if I do it for the system, then those forces are internal, and Newton's second law doesn't give us any way of doing that. Okay, so not when I write it for the whole system. So what we can do for starters is we're going to imagine the ropes that are tying M2 to M3 and M1 to M2. We're going to imagine them to be massless, and that's pretty reasonable. A rope normally weighs quite a bit less than the things it can carry, so we're going to assume those are massless, so that won't be a problem. But we can, by necessity, go ahead and treat the whole thing as one object. So let's start off with solution. The equations we need are the summation of the forces is equal to mass times acceleration. And of course, that's a vector equation. So that means there's an x equation, there's a y equation, and it could even be a z equation. We're going to make use of that, but we're going to say first, treat the train of boxes as one object. So we're actually applying Newton's second law as if this is one big object. And the reason why we're going to do that is we're going to see that that's a really quick and dirty way to get the acceleration, but it leaves us no method of getting the actual tensions in the ropes. So I'm going to go ahead and do that. I'm going to say the summation of the forces in the x direction is equal to mass times acceleration in the x direction. Now, the reason why I'm only doing the summation of forces in the x direction is this doesn't have any friction, and we can guess, since none of these ropes are pulling in the upward direction or in the downward direction, we can guess that the normal force will not be affected. Unlike the last one, where notice the normal force turned out to be not just the weight, the normal force would have been 98 newtons, but because the 40 Newton pulling force pulled up at a 30-degree angle, it was able to assume a little bit of the role that the normal force would otherwise do. So we ended up getting 98 minus 40 newtons, and that gave us the 58, or excuse me, the 78 newtons. Actually, I said 98 minus 40. I meant 98 minus 20. Okay, so that would be the only reason we do the y component, is if we wanted to figure out what the normal force is, and if we later, which we'll learn later, if we wanted to do friction, friction is directly proportional to the normal force, so we would need it for that. I don't need it for that because there's no friction, and y'all haven't learned about friction yet either. So summation of forces in the x direction equals mass times acceleration in the x direction, again for the entire object. Now the entire object is mass m1 plus the rope, which is massless, plus mass M2, plus the other rope, which is massless, plus M3. So if you add M1 plus M2 plus M3, you get 15 plus 20 is 35, plus 10 is 45. So what we're going to get is 100.0 newtons in the positive direction, because I'm just going to go ahead and say this. So that's one way you can write off to the side of your notes, just write Y and an X and show them like that. That tells everybody, hey, I'm treating to the right as the positive X direction. I'm treating up as the positive Y direction. And later when we learn about torques, you'll draw a little counterclockwise or clockwise circle and you'll just put a plus symbol in it. So sometimes you'll see people will write like this, and that just means, hey, anything going to the right is positive X direction. Anything going vertically upward is the positive Y direction. And anything rotating counterclockwise would be considered a positive torque. That's the symbol that we can use for that in your statics classes as well as in physics. So that's sort of what I'm doing here. So that's why I called the 100 newtons 100 newtons as opposed to negative 100 newtons, because I'm assuming to the right is positive. That is the only force acting because it's frictionless. Okay. So that's given to us as the total force is equal to 100 newtons. But the mass we said was what, 35 plus 10 be 45. So this would be 45.0 kilograms times A. That's it. We're now ready to solve for A. It's that straightforward. So now I can say that A is obviously equal to 100.0 newtons divided by 45.0 kilograms. Now, 45 goes into 100 twice and leaves 10 left over. So that'd be 2 and then 10/45. 10/45 doesn't really jump out at me as anything super easy to calculate. I could break it down to 2 ninths. So that'd be 0.222. So we're going to call this 2.22 meters per second is the acceleration, and I've carried one extra digit beyond the sig figs there. So by treating the train of boxes as one object, I was able to compute the acceleration all by myself. And now, if we go on the assumption that the ropes are not going to stretch and they're not going to get loose and get slack in them or whatever, then that means if I move the mass M1 to the right by 1 inch, the mass M2 is going to move to the right by 1 inch, and the mass M3 is going to move to the right by 1 inch. This is a long, detailed explanation that you got to pay attention to. I apologize for that. So if I move using this 100 Newton force, if I move M1 to the right 1 inch, M2 is going to move to the right 1 inch, and M3 is going to move to the right 1 inch. If I move M1 to the right 1 inch in 1 second, then M2 is going to move to the right by 1 inch in 1 second, and M3 is going to move to the right by 1 inch in 1 second. So that in fact, the velocities of M1, M2, and M3 are all the same. So that was part of it. I'm arguing now. I just finished arguing that the velocity of M3 is going to be the same as the velocity of M2, and that's going to be the same as the velocity of M3. Now, if I pulled M3 1 inch in the first second and then 2 inches in the second, then M2 is going to move 1 inch in the first second and 2 inches in the second. And M3 is going to move 1 inch in 1 second and 2 inches in the second. And what that tells us is the acceleration of M3 is equal to the acceleration of M2, and that's equal to the acceleration of M3. Okay. So by that, I now can say 2.22 is exactly the acceleration of M3, M2, and M1, even though I calculated it for the whole chunk of mass. Now, I just want to double check, make sure my division in my head was right, and that is 2.22. So we're good on that. Now I'm going to go ahead and consider the individual free body diagrams for the individual masses. So I'm going to draw a little coordinate system for each of those. And this is an important part that you have to understand because we're going to work with tensions over and over again. And you got to figure out some ways of dealing with tension. So, first off, right here, this is mass M3, and M3 is 10 kilograms. Now, acting on this is a force in the upward direction that's called our normal force. So I'll call that Fn3. And acting in the downward direction is the weight. I'll call that weight 3, which of course is equal to 98.0 newtons because it's just 10 kilograms times 9.8. Now, in addition to that, we have a tension acting to the right, which is the positive direction, and that tension shall be called T3. Okay? So that's the free body diagram for box M3. Notice there's no other forces acting on it. If there was a force going to the left, that would be like friction or something like that, but this is supposed to be frictionless, so I won't have that. Now I'm going to draw a coordinate system again. This time it's for M2. And for this case, I've got M2. And of course, M2 is the 20 kilogram one. So that's 196 newtons is the actual weight. So this is W2 equals 196 newtons. And we've got a normal force that would be called Fn2. But remember, M2 says, man, I could really move to the right pretty well if it wasn't for this stupid rope behind me slowing me down. So that tells me that T3, the rope that was pulling M3 to the right, is pulling to the left on M2. So that means I have to draw another force right here, and that force is T3. I should go ahead and write right up here. I'll say this is T3 and this is T2, just so you know on the diagram where it is. Now, additionally, M2 says, hey, the M2 is, I'm being pulled forward by T2. Yeah, go ahead, Michael.
I just want to clarify. So when you're referring to W3, 2, or 1, that's the equivalent to mg.
Exactly.
Okay, okay. I just wanted to make sure because
Yeah, yeah. I try to use W. Your book is using F sub G, but that's
yeah.
why I pointed that out, just because I think W is a little easier and have to work with subscripts every time.
Okay, cool. Thank you.
Yeah, good question. Okay, so now I'm going to draw a free body diagram for M3 as well. And there's my X, and there's my X, and there's my Y, and there's my Y. And this time we have mass M1, which is in fact 15 kilograms. And that means the weight is W1 is equal to 147 newtons. The normal force Fn1, which we could work out with the summation of forces in the y direction. We just have to realize the summation of forces in the y direction is zero, just like it was before, because these boxes are only going to slide perfectly horizontally, which means the y is never changing. Since the y is never changing, the velocity is zero, and since the y never changed, the velocity is still zero and still zero and still zero, so the acceleration is zero. Now, according to M1, it has a force pulling to the right, and that force, oh, I forgot something on diagram two. I'll do that in a second. But the force pulling to the right was the 100 newtons, and that is in the positive direction. So I'm going to put 100.0 newtons. And then if you asked M1, it would say, hey, I could be going pretty fast if it wasn't for this rope behind me that's slowing me down. And that rope behind me is what I'm missing on the other diagram. So remember what M2 says is M2 says, hey, I could move pretty well if it wasn't for this rope behind me that's slowing me down because I have to pull M3 with me. But what's making M2 move is T2. So I can also put over here T2 is that tension. Now, this is the whole point of me doing these three so that you'll see in the two diagrams, T3 points to the right in the first diagram and it points to the left in the other. That's the norm. when you're going to try to work out tensions from the perspective of two different bodies on opposite ends of the rope, the tensions will be in opposite directions. So just that's something you got to learn that eventually you can convince yourself that you're right about it, but right now you just got to suck it up and say, I'm going to commit this to memory and hopefully I'll make sense of it later. Now, similarly, the M1 says that T2 is pulling backwards on me, so I have to add this right here and say that's T2. Now, again, I could do the summation of forces in the y direction to get me Fn3 and Fn2 and Fn1. Of course, you'd obviously see that Fn1 is just going to be 147 newtons. Similarly, you'd see Fn2 is going to be 196 newtons. And similarly, you'd see that Fn3 would be 98 newtons. But I don't have to do any of that. I'm going to go ahead and do the summation of forces in the x direction. So the summation of the forces in the x direction equals mass 3 times acceleration in the x direction. And that's the only direction acceleration goes. So I'm not going to waste my time putting a subscript x on the acceleration a. I'm just going to take my free body diagram and write out what F is and write out what M3 is. So the force is just T3. So I'm going to say T3, which points in the positive direction. So it's a positive T3, is equal to M3, which is what we found was 10 kilograms, times A. I'm going to call this equation 1. Okay, it's a good thing to get in the swing of whenever you make up an equation, go ahead and number it so you can refer to it. Because what's going to happen is a large part of this course is you taking multiple equations, putting them all together to solve for multiple variables. And you should know the fundamental rule of algebra is if you have five unknowns, you need five different equations to be able to solve it. And in fact, if you have six, it might actually make it unsolvable. It could also just make it, one of the equations redundant or whatever. But the main thing is if you have n variables, you need n equations. So in this case, we've got variables of acceleration, which we've already found that, and we've figured out that A1 is equal to A2 is equal to A3. This allows us to figure that out as well. But we also have T2 and T3. So there's unknowns there, and we need a lot of equations. So I'm going to go ahead and number this one so we can refer to it later. One of the reasons that you number it is because when you're going to solve the system of equations, you know that if you have three equations and three unknowns, you better use each of the three equations. So by calling one equation equation one, another one two, and another one three, and then writing, I'm plugging equation one into equation two, or I'm multiplying equation three by this and adding it to equation two. By having statements like that, you can see whether or not you've used all three equations, because there is chances where you can accidentally skip using one of the equations and the algebra will just magically make a mistake so that it gives you an answer, and you'll get an answer that's completely wrong and you'll not even know it. So keeping track of that will help. Now I'm going to do the summation of forces in the in the x direction is equal to mass times acceleration for number 2. So summation forces in the x direction equals m2 times a. In this case, I see that I have a tension T2 acting in the positive direction, so I'll say T2. And then I have a T3 acting in the negative direction. Again, rather than writing plus a negative number, I'm just going to write it as subtraction. I'm going to say T2 minus T3 is the total force on the left-hand side. That's equal to M2, which is 20.0 kilograms times A, and I'm going to call that equation 2. Similarly, I'm going to do the same thing with with mass 1. So in this case, you see that I have a 100 Newton force acting to the right, so that's going to be a positive. And then I have a T2 acting to the left, so that'd be plus negative T2, which I'm just going to call minus T2. And then all of that's equal to M1, which M1 was the 15 kilograms, so that's 15.0 kilograms times A, and that's going to be equation 3. Okay? So what we can do is we can plug equation 1 into equation 2 just by it's already solved for T3, so I can just replace T3 with the right-hand side. So I'm going to say plug 1 into 2, and that tells us automatically, okay, I've used equations 1 and 2. When I plug them in, I'm going to get T2 minus 10.0 kilograms times A is equal to 20.0 kilograms times A. So that's a little closer. I'm going to call this equation 4, and I'll just keep it there. Now I'm going to solve for for T2 and plug it into equation 3. Okay, now you can see by my sentences I've used equations 1, 2, and 3 once I've done this. Solving for T2 gives me T2 is equal to 10.0 kilograms times A plus 20.0 kilograms times A, which equals 30.0 kilograms times A. So this is what I'd call equation 4 prime because it's the same thing as equation 4. I just solved it for a different variable and combined like terms, so I just called it 4 prime. Now I'm going to plug 4 prime into 3, so I get 100.0 newtons minus T2, which is 30.0 kilograms times A is equal to 15.0 kilograms times A, and I can add 30.0 kilograms times A to both sides. And when I do that, I get 100.0 newtons is equal to 30 plus 15 would be 45. Whoa. Would be 45.0 kilograms times A. So lo and behold, we get A is equal to 100.0 newtons over 45.0 kilograms, which gives us again 2.222 meters per second every second. And that's our acceleration figured out a different way. So you can see, even if I just never even did it as if it's one big object, I could still get the acceleration. But in addition to that, I'm also able to get the individual tensions. So I did confirm that the acceleration is the same. Now that I have the acceleration, I can use equation 1 to figure out T3. So uh, using A equals 2.222 meters per second every second. And T1, I have, or excuse me, and equation 1. And 1, I have T3 is equal to 10.0 kilograms times 2.222 meters per second, which gives me, of course, 22.22 newtons is equal to T3. So that's part of answer B. Actually, I think yeah, that is part answer B. Okay. Now I can do the same thing with equation 2 with 2, or actually with 4. The reason why I'm doing 4 is because actually 4 prime is even better. So 4 prime I've already solved for T2, so it's really smart to use that. So in this case, I'm going to say T2 is equal to, notice from 4 prime, T2 is equal to 30 kilograms times A. So 30 times 2.222, whoa, meters per second gives me 6.666, but in this case it'd be 66.66. So this would be 66.66 newtons is equal to T2, and that is our answer for part C. Any questions on that? Okay, so that's sort of one of the more quote unquote complicated, just in terms of being complicated the first time you do it. Hopefully, now you know how to do it. No matter how many boxes it would be, you can always solve for all the individual tensions. But does anybody have any questions on that? Anything you don't understand?
I do have a question.
Okay.
So you know how you split it up into two parts?
Mm-hmm.
We find the acceleration in A. It kind of worked for this example, but for other examples, could we just plug A into the equation for one and two
Yeah,
instead of doing,
absolutely. The
okay.
only reason why I did it this way was to show you that you didn't have to do it by first taking the whole object.
Okay, I see. I didn't know
And
if
it,
it was like a situation dependent thing.
no, no, it pretty much always works. The big thing is when you do it as one big object, you just can't determine the individual tensions.
I see.
So in my estimation, I hardly ever will take a big object and made of multiple parts and treat that as one object. I very rarely do that when I'm just solving Newton's second law problems. As
Okay.
the semester goes on, when you're doing momentum problems and stuff like that, there's sometimes a very good reason to treat all the objects as one big system. But other than that, you pretty much are always better off just doing it individually. Okay. Now, in light of that, we're going to do another problem that's a very famous one. It's called the Atwood machine. And now this is equivalent to example 413, but I'm just going to do it with symbols and I'm going to work it out. And that way, I'm just going to call it example as opposed to calling it example 2 or 3 or whatever. Uh, excuse me. I meant to write one there. So that was example 1. Now I'm going to go ahead and do example 2. Again, this just means example 2 because it's not one that's exactly in the book. It's one that I'm making up. So let me show you what I mean. I'm going to attempt to draw a really nice pulley. Look how perfect the circle I drew. I was using the little cheater thing. Okay. So that's a pulley. And right now we're going to pretend that pulley is massless and frictionless. As the semester goes on, we'll learn about torque, we'll learn about friction and stuff like that, in which case we can remedy this and include a pulley that is both massive, meaning it has a mass that's not zero, and friction full, meaning it has some friction, and we can still calculate the acceleration. We're just not going to be able to do it yet. Okay. So, what I'm going to do is I'm going to hang a string. Imagine it being looped over the pulley, and on one side, I'm going to have a really big mass, and that is mass capital M. And then on the other side, I'm going to have a really small mass, and this mass is lowercase m. Okay. What are the accelerations and the tension in this Atwood machine? So the Atwood machine is actually a physical object that is something we use a lot in physics. And Therefore, I wanted to go ahead and write and call it the Atwood machine so you'd understand what an Atwood machine is. I want to know what the accelerations and the tension are uh, in this Atwood machine. Assume the pulley and strings slash ropes are massless and that the pulley is frictionless. Now, what we mean by that is not only are the bearings in the pulley so perfect that no friction happens from it, but also the rope that goes over the rope or the string that goes over the pulley is not going to feel any friction between it and the pulley itself, nor is there going to be any sliding. That's another thing that's going to be important. Right now, it's not important because we're not calculating the acceleration, the rotational acceleration of the pulley, but later that would be a problem. So you might say to yourself, why are we making the pulley massless and why are we making the pulley frictionless and all that good stuff? As I told you, there's very good reasons. Specifically, we can't deal with torque right now because we haven't learned that, and we haven't learned friction yet. But additionally, what I want to show you is that if the string were not massless, then as looking at this, it appears because I used a big M in one case and a small m in the other case, it appears that the mass on the right is going to fall down really fast. And if you tried to calculate the tension in that string on the right hand side, you'd say that tension is just the force in the string that's keeping the mass, the big M, from falling at 9.8 meters per second per second. But if you look on the other side of the pulley, that same rope is lifting up the little mass M, and therefore on that side the pulley would be, or excuse me, the string would actually have a tension that's big enough to accelerate the mass M upward at the same acceleration of the mass big M. And the tension on the right hand side has to not only slow down the mass big M, but it also has to pull the weight of the pulley around. So you would see that the tension on the right would be slightly bigger than the tension on the left. With this case, you don't have to deal with any of that because the pulley is frictionless and massless, so the tension on the left is going to be equal to the tension on the right. But we can make the same arguments that I made before regarding those tensions. For instance, if the pulley or if the mass on the right moves down 1 inch, the mass on the left moves up 1 inch. If the mass on the right moves down 1 inch in 1 second, then the pulley on, or excuse me, the mass on the left goes up 1 inch in 1 second. That means the velocity of big M is the same in magnitude as the velocity of little m. If the mass on the right, big M, moves 1 inch in 1 second and then 2 inches in the next second, then the little m is going to move 1 inch in 1 second and 2 inches in the next second, and therefore the accelerations are the same. And that all is dependent on just the fact that the pulley can't, the ropes or the strings can't stretch, they're not going to lengthen, nor are they going to become slack. So long as we assume that the pulleys are not going to become slack and that the string's not going to stretch, then we see that A for capital M is the same in magnitude as A for little m. That's important. And in fact, we want to make our coordinate systems consistent with that. For instance, if we called downward direction negative, then the acceleration of the big M would be positive and the acceleration of the little m would be negative. But that would make us have another equation where we'd have to have an equation that relates the acceleration of little m to the acceleration of big M. But if we make our coordinates consistent from the left side to the right, and I'll show you how to do that in a second, then we don't have to have another equation relating the acceleration of little m to the acceleration of big M. So how do we do this? Well, it starts by drawing a free body diagram for each of the masses. Okay, so let's draw a free body diagram for each of the masses. Now I'm going to say this is the mass little m. Oops. This is the mass little m. And it has acting on it I'm going to consider up on the left-hand side to be positive. And then notice if you go up the left-hand side of the pulley and then ride the pulley, you're then going to go down on the right-hand side. So going up on the left is equivalent to going down on the right. So that's how I'm going to make sure my two accelerations are right. I'm going to use up as the positive direction for little m, and I'm going to use down as the positive direction for big M. So now I can write Y right here, and that means I have a tension T pulling the mass little m up, and I have the weight due to gravity pulling down, and that is lowercase m times g. So if I choose to write the summation of the forces in the y direction equals mass times acceleration in the y direction, that's going to be the only direction, so I need not subscript at y anymore. But in this case, I'm going to get equation one is t minus mg is equal to ma. So that's equation one. Now I'm going to do a free body diagram for big M. But remember to make my accelerations the same for both. That means I got to put y pointing downward for this one. And in this case, I got a mass big M. Now, according to this side, the weight pulls downward, which is the positive y direction. So I'm going to draw this as W sub M is equal to mg. And if you asked the mass M, it would say, man, I would fly it down at 9.8 meters per second every second if it wasn't for the stupid rope slowing me down. And that teaches you that the rope or the string is acting in the upward direction. And again, I call them both the same thing because in order for them to be different, it would have had to be a different force on one side than the other. And that would come from like the pulley having a mass or the pulley having some friction. So we don't have to deal with that. But now I can write the summation of the forces in the y direction equals mass times acceleration in the y direction. In this case, we get big mg minus t is equal to big M A, and that's equation two. So this is one of the main reasons that I'm solving this problem, because one thing that you'll run into over and over is solving systems of equations. And generally, you probably did learn this in, pre-calculus algebra. But if you have two equations that have the same unknown in both of them, and one of them has a coefficient of, let's say, -3, and the other one has a coefficient of +3, then a smart way to solve that system is to add the two equations together, because that variable is going to disappear, because one's a 3t and the other one's a -3t. 3t plus -3t is 0t, so you've gotten rid of the t. That's what I'm going to use here. So I'm going to say add equations 1 and 2. And what I mean by that is I'm going to add the left-hand side of 1 to the left-hand side of 2, and I'm going to add the right-hand side of 1 to the right-hand side of 2. I'm going to show it more explicitly than I normally do when I'm doing the work just this first time. So what I'm doing is t minus mg plus mg minus t. Now, if I happen to have subtracted, then I would really need those parentheses that I put around mg minus t, but I was adding this time, so I didn't really need it. But I wanted to point that out to you. So if you choose to subtract one equation from the other, you've got to remember that that subtraction, that negative symbol, is going to have to be distributed inside the parentheses. So it's smart to put the parentheses around it. In this case, I'm just adding, so I didn't need to, but I wanted to stress that to you. Now I add the left-hand side, or excuse me, the right-hand side of 1 to the right-hand side of 2. You can see that it's MA plus MA, And again, I'd put that second one in parentheses in case I happen to subtract. In other words, if you had mg plus t and t plus mg, in there, you would actually want to subtract the two because one t has a coefficient of positive one and the other t has a coefficient of positive one as well. So by subtracting them, one of them would cancel out. And if you chose to do that, you would really need to be very persnickety about making sure your parentheses are correct. So I can now take this equation and I see that T minus mg plus big Mg minus T means the T's are going to cancel each other out. Okay. And not only that, I can see that I have a common factor of G with what's left. So the left-hand side is going to become M minus little m times G. So that takes care of this is where I got the big M G being positive, and this is where I got the little m G being negative. So I can check those off. The same thing's going to happen to the right hand side. I've got a MA and a big MA, so I have a common factor of A. So in this case, I'm going to go ahead and write equals big M plus little m parentheses A. And now since we gave you the big M and the little m, you can go on the assumption, and that's what you're supposed to do. You're going on the assumption that you know the big M and the little m, and what you're trying to solve for is the acceleration and the tension. So we know that M, the big M, and the little m are both known quantities. G is a known quantity. So what I have right now is the ability to solve for A. And what we get is A is equal to M minus M over m plus m, and all of that times g. So that's our acceleration. And that's a wonderful way to express it. Notice I have in parentheses a dimensionless or a unitless quantity, m minus m over m plus m. M minus m, both of those have units of kilograms, and when you subtract them, you therefore get kilograms. M plus m both has kilograms. When you add them, you have kilograms. So that means the numerator's in kilograms, the denominator's in kilograms. When you divide the numerator by the denominator, you get no units because the kilograms cancel out. And then what's left is a single number, in this case g, which has exactly the units of acceleration, which is exactly the units of A is supposed to have. So by writing it this way, it's obvious to anybody that looks at it that this is dimensionally correct. So it's really nice to be able to write the equation that way. Now that we have that, we can plug this A into either of these equations, equation one or equation two, and solve for T. And that's what I'm going to do. I'm going to plug A into one. And the reason why I'm using one is because the tension is already positive there. So I don't have to, multiply or divide by any negatives. So it's kind of nice. So what I'm going to do is say T minus mg is equal to ma, which means T is equal to m times g plus A, because once I get the mg on the other side, it's mg plus ma. Both of them have a common factor of m, so why not factor it out? That's what I did. And that actually makes it a little easier in going forward because now I can say m times g plus now a is m minus m over m plus m times g, and that's going to force me to make this parenthesis into a square bracket because I'm obsessive compulsive. Okay. Now I can factor out this common factor of g, and in so doing, I get t is equal to big lowercase m times g times 1 plus m minus m over m plus m, like that. Now I can use just a regular parenthesis, but in order to make this the simplest thing possible, I'm going to get a common denominator by multiplying the 1 by m plus m over m plus m. So that's going to give me mg times m plus plus, remember, fraction bars are actually grouping as well. They're parentheses. So when you're adding, for instance, a fraction, that's equivalent to adding parentheses around the numerator. So I'll just do that to show you that this time, even though it's not really going to matter because this is addition. But if it was subtraction, it would definitely matter. And then, of course, the common denominator was big M plus little m. And now, of course, I have a reason to do the square bracket because I got a parentheses inside. Either way, that's going to give me m times g. And now I can see the m plus the big M is going to give me 2m. And then the m minus the little m is going to give me 0. And then all of this is over m plus little m. So what we can see is that the tension, T, is going to be equal to, in this case, I can say, yeah, I'll do it this way. I'm going to say 2 times m like this over m plus m. Notice that's a dimensionless quantity. And remember, I told you one of the nicest ways to solve equations is to have a dimensionless quantity multiplied by something that's obviously got the right units to it. The tension should have units of force. And for instance, weight is a force. So M times G has units of force. And in fact, what I'm going to do is take the big M and multiply it by the G. And now I've got it solved in a convenient way. And that's the tension, 2m over m plus m times big MG. Okay. So that's how you solve an Atwood machine. Anybody have any questions on that? So notice you have to draw a free body diagram for each of the objects. Then you have to solve the system of equations. But before you do that, you want to try to make the two coordinate systems on the opposite sides of the pulley consistent with one another. In other words, whatever you consider a positive direction on one side, you have to figure out what that results in on the other side, and that should be the positive direction for that one. So, for instance, when I decided lowercase m going up was a positive direction, that meant uppercase M going down had to be a positive direction. And that just frees us up from having to write A big M is equal to negative A little m, which is just another equation to deal with, and you don't want to deal with that. So by linking it this way with these coordinate systems, you get a much easier problem to solve. Anybody have any questions on that? All right, let's look at a conceptual example 414. It says conceptual example 414. Hopefully all of y'all have your book available. I'm going to be reading it to you, but it says a mover is trying to lift a piano slowly up to a second story apartment. He is using a rope looped over two pulleys as shown. What force must he exert on the rope to slowly lift the piano's 1600 Newton weight? So what we're looking at here is basically a piano which has a force pointing down like this. That's M times G. That's 1600 newtons is M times G. But acting on it as well is a force of tension on the right due to the right hand side of the pulley, and then a force of tension on the left due to the left hand side of the pulley. By necessity, if the pulley is considered massless, and obviously a pulley compared to a 1600 Newton uh, piano is definitely going to be a small mass. But if the pulley's frictionless and massless, then the two forces across the tension on opposite sides have to be equal in magnitude. So what we have is Ft plus Ft, which would be 2Ft. That's the force due to tension. So 2 times the tension is equal to mg is what would be required to just keep it at equilibrium, to keep it from falling. But if you wanted to actually accelerate it upward, then you'd have to have the 2 times the tensions is bigger than mg. But the main thing that I wanted to point out for this is so that you'd see when you have a pulley set up like this, so that you have a rope on each side, then that doubles your force by a factor of two. Now, you're not getting something for nothing because if you actually worked out the mechanical advantage here, the mechanical advantage is that you're doubling the force. So by him pulling up on that or pulling down on that pulley up at the top, he only has to supply a force of that's equal to the tension. And because that pulley down at the bottom's there, he gets twice as much force out of it. But here's where you lose this is where you lose something from doing this. Every inch that he pulls that rope down, the rope on the two pulleys down there is only going to go up half an inch. So he has to pull it 2 inches to make it move 1 inch. So he literally has to move twice as far. And that's the mechanical advantage. The mechanical advantage is he's multiplying the force by two, but he's also decreasing the distance that he pulls it by a factor of two as well. So basically, we'll learn something called work, which is force times distance, and that's equivalent to energy. And in order for you not to make up energy where there wasn't any, the work in must be equal to the work out. So two forces times 1 inch is the same thing as one force times half an inch. So that's why it doesn't pay off any more than that. You are getting an advantage. Specifically, you get to lift a piano with only supplying 800 newtons of force, or a little bit more than 800 newtons of force. But you're going to have to, if you want to move the piano up, let's say 10 feet, you're going to have to pull it 20 feet to get it to go 10 feet. Not only that, the tension in the actual crane boom that you see in that picture, those tensions are two tensions, and therefore the crane is going to have to hold up twice as much weight. It's making up for the extra force that you didn't have to put in. It's got to compensate for that. So, any questions on that one? All right, so now I'm going to move to example 415, which I call the fuzzy dice example. Example 415. Your book calls it an accelerometer, and it really is. So here's the picture. It says a small mass, lowercase m, hangs from a thin string and can swing like a pendulum. You attach it above the window of your car as shown in figure 425A. When the car is at rest, the string hangs vertically. What angle theta does the string make? A, when the car accelerates at A equals 1.20 meters per second every second, and B, when the car moves at constant velocity of 90 kilometers per hour. So, uh, doing this, one, I want to show you this because it's a neat trick that you normally don't learn in Algebra 1, Algebra 2, or pre-calculus algebra or pre-calculus trig. It's a new technique of solving a system of equations that you likely didn't learn from mathematics because mathematicians have very strict rules. And one of the biggest rules they know about are that you've probably run into with mathematicians is never divide by zero. So they never teach you anything related to dividing one equation by another, usually. The reason why is because you could accidentally divide by zero and get completely hogwash results. When you actually divide by zero, or even like if you remembered the early days of algebra when they said whatever you do to an equation, you're allowed to do it as long as you do it to both sides. Well, the caveat was that was you weren't really allowed to multiply by zero on both sides either, because if you multiply by zero on both sides, you're going to get zero equals zero, no matter how true or not true the equation was, and in fact, you can get false solutions. So it's always a danger when you're blindly multiplying symbols or when you're blindly dividing by symbols, because those symbols might turn out to be zero and you could get statements that aren't true. So that's the big caveat that you got to keep in mind. the lucky thing is that in the physics world, most of the time, the problems that we're interested in have no possibility of being zero because if they did, they wouldn't be physically important to us. So we can a lot of times skip that worry and worrying about dividing by. You always have to think about it though. Every time you divide an equation by another equation, you have to think under what conditions is that divisor going to be zero. And the same thing's true if you multiply both sides of an equation by a symbol. You got to think under what conditions would that symbol be equal to zero because that could be a problem. All right. So here's the problem. I'm going to draw basically what's going on here. We have a string with a mass m hanging from it. And what's going to happen when the car actually accelerates is that string is going to be tilted back some angle theta. Okay. So, uh, car at rest, and this one is the car accelerating. So, the car accelerating that way is what's going on. So, that's the scenario. I really should draw one of these as if it's hatched or something like that. So, maybe I'll do a little line like that, a little line like that. And there you can see that we're just imagining that it was initially hanging straight down, but now the reality is it's tilted back at an angle A. So what I'm going to do is draw a free body diagram for this. So here's my free body diagram. There's X, there's Y. Here's the mass M, and the forces acting on it. One force you know for sure is the weight. And of course, that's automatically aligned along the negative y-axis because I chose to make my axes vertical and horizontal. So this is W is equal to mg. Now, in addition to that, I have a force, which is the tension in the rope, and that makes an angle theta with the vertical. Now, the other thing to recognize here is that the acceleration is A and it's going that way. Okay, so this is part A, really. Part B, they're going to say it's not accelerating, it's moving at a constant velocity, and we'll deal with that. But first off, I've got to now take this blue vector and convert it to components in the X and Y direction. So again, if I imagine going from the tail to the head by only going along X and Y directions, then you can see that if I go first Y and then X, I'm going to go up for Y and I'm going to go right for X. Alternatively, if I first did X, I'm going to go right for X and then up for Y. You can see that I get the same result both times. Now, with that in mind, I can go ahead and say that this is the tension in the X direction and this is the tension in the Y direction. And now, again, keeping my training wheels on, I can write in the cosine of theta is equal to adjacent over hypotenuse. And in this case, the adjacent is ty and the hypotenuse is t. So ty is going to equal positive t cosine theta. Similarly, keeping the training wheels on, sine is equal to opposite over hypotenuse. The opposite is going to be t sub x, and the hypotenuse is going to be t. So this says t sub x is equal to positive t times the sine of theta. So now I'm going to use the summation of the forces in the x direction equals mass times acceleration in the x direction. And what we're imagining here is there's some period of time where the car is accelerating at a fixed acceleration. Specifically, your book is saying a equals 1.20 meters per second. So I should write that down over here. Meters per second is what a is. And they didn't give us a mass, they didn't give us an angle. And then part B, they said V is equal to 90 kilometers per hour. That's not even going to matter, but I wanted to write that down there. Now, the summation of forces in the x direction, I think you can see you really only have one force in the x direction. That force is T sub x, so that gives me T sine theta is equal to m times a. And that's really the only acceleration because I'm imagining the car moving at a constant acceleration to the right, and that's going to cause the string to go back like this, and it'll stay at exactly that angle. If it was accelerating and then the acceleration was changing, then it would swing back and forth and stuff like that. But I'm imagining some small interval of time where the acceleration has been constant long enough where the mass reached this equilibrium point and hung out there. And that's what I get for equation one. The summation of the forces in the x direction is equal to mass times acceleration in the x direction. Now I've got to do the same thing for the summation of forces in the y direction. So the summation forces in the y direction equals mass times acceleration in the y direction. Now, in this case, I've got to remember that, or I've got to remind you that the acceleration is a constant acceleration, and the mass on the string has reached some equilibrium at an angle theta. So the y is not physically changing. It's going to stay at that fixed height. And therefore, y is not changing. And therefore, the velocity in the y direction is zero. But if you wait a couple seconds, it's still zero. And if you wait a split second later, it's still zero. So that means the acceleration in the y direction is equal to zero. So now all we have is T sub y is pointing in the up direction and mg is pointing in the down direction. So F equals ma in the y direction becomes Ty minus mg is equal to zero. That's equation two. But it turns out oh, excuse me, Ty. Uh, I should go ahead and write what Ty is, which is T cosine theta. So let's write T cosine theta minus mg is equal to zero. And that's still equation two. But to make it a little better, I'm going to go ahead and call this equation two prime. And what I'm going to do is say T cosine theta is equal to mg. Notice all I did was added mg to both sides. Now, here's the part where I'm teaching you another technique that you probably hadn't heard from in your math classes. Okay. So, what I'm going to do is divide equation one by equation two. Again, this is something your math class often won't teach you because they're very concerned about you accidentally dividing by zero, and that is a real concern. So you got to keep it in your mind. But it's pretty straightforward, and look how wonderful it works out. So if I take one and divide it by two, that becomes T sine theta is the left-hand side of one, and I'm going to divide that by the left-hand side of two, which is T cosine theta. And that's going to be equal to the right-hand side of 1 divided by the right-hand side of 2. Well, the right-hand side of 1 is m times a, and the right-hand side of 2 is m times g. So you can immediately see that the m's cancel out, and you can also see that the t's cancel out. Not only that, I suspect somebody might know an identity for sine theta over cosine theta. Anybody? So sine theta divided by cosine theta. Remember that would be opposite over hypotenuse divided by adjacent over hypotenuse. So you end up getting opposite over adjacent, which is tangent. So tangent theta is equal to A over G. And what they asked for here is what angle theta does the string make when the car accelerates? So theta is equal to the inverse tangent of A over G, like that. And of course, for our particular acceleration, that's going to be the inverse tangent of 1.20 meters per second divided by 9.80 meters per second. And of course, when I take the inverse tangent of that, I'll say shift tangent inverse 1.2 divided by 9.8, close parentheses, got it in degree mode. That gives me 6.981 degrees. And that's the angle. Of course, I only had 3 sig figs, so this one is not a sig fig, but that is theta. Any questions on that one? Okay. So if you go back and look at this and use the estimate that in part B, A is equal to 0, then look what happens. If A equals 90 kilometers per hour, then A is equal to 0. I think I said A. If the velocity is equal to 90 kilometers per hour, then the acceleration is 0 because it's moving at some constant velocity, 90 kilometers per hour. Therefore, equation 1 is going to become just T sine theta is equal to 0. And all of that means that tangent theta is equal to 0 over G. Therefore, theta is equal to 0 degrees. And that's really what's going to happen. As long as you give it time to reach equilibrium, the thing will fall back down and hang perfectly vertical. In reality, when you do that, once you stop accelerating, it's going to fall down and wiggle back and forth like this until friction forces and air resistance and all that brings it to a stop, assuming that you're driving so smoothly that it's not going to make it shake anymore. But that's really the goal here is when it's accelerating, you will get it leaning at an angle. And in fact, if it was accelerating in reverse, the angle would be towards the windshield as opposed to towards the back seat. Anybody have any questions on that one? All right, so that's a really good example regarding this. Now, we've got one more major type of problem to understand with Chapter 4, and this problem is related to inclined planes. And this is teaching you something as well. In this case, we're going to learn how to use some rules from geometry to actually figure out components of forces. This is something that's going to have to happen over and over and over and over again. So you really got to learn it this time. So we're going to do example 416. And example 416 says a box of mass M is placed on a smooth, frictionless incline that makes an angle theta with the horizontal as shown. A, determine the normal force on the box. B, determine the box's acceleration. And C, evaluate for a mass M equal 10.0, or actually it just says 10 kilograms, and an incline of theta equals 30 degrees. So let me first off draw the diagram. So we're going to imagine this is an incline. It's got an angle theta. And we're going to imagine that a box is sitting on that incline and its mass is M. Okay. Now it turns out that when you have an inclined plane like this, a lot of physics can be simplified if you actually use a tilted coordinate system. So that's what we're going to use. We're going to draw a free body diagram with a tilted coordinate system. So here's my tilted coordinate system. And of course, I still want my X and Y axes perpendicular to each other. You don't technically have to have that, but it certainly makes life a little easier. So I'm saying this is X prime axis and the Y prime axis is tilted up and to the right. The mass right here is just plain M. So I'll put that there. Now, what we know is that the weight is acting vertically downward, but that's not parallel to one of our axes. So I can't put it as red or green or even blue because sometimes I use the positive direction. I use blue for that. I don't know why I told you that, and I don't know why. I'm going to try not to do it. But, anyways, I'm going to just draw this weight vector W. I'm going to draw it vertically and say weight is equal to m times g like that. Okay. Now, in addition to that, I know for a fact that there's a normal force supplied by the inclined plane. If it wasn't a normal force, then the box would just break through the plane and fall through. However, in this case, the normal force is parallel to an axis, and in fact, it's parallel to the y prime axis. So I'm going to use my green vector because that's the positive direction, and this force is Fn. Okay. Now, if there was friction, if this was a frictionless surface, a friction full surface, then you might want to draw a force like this for the friction force. But you got to remember, hey, if I put a box on an inclined plane and the inclined plane's frictionless, then the box is going to slide down the incline. And in sliding, it's going to actually accelerate. So there's got to be some kind of force acting parallel to the inclined plane. And right here, it doesn't show it. Now I'm going to show you where that force comes into play. What we do know, for instance, is the angle that the inclined plane and therefore the x-axis makes with the horizontal is the angle theta. So I've got to work out a little geometry here for you to figure out all this stuff. But for starters, there is a right triangle right here because this is vertical and this is horizontal. That means these two make a 90-degree angle. And this would be the angle of the incline. Because of that, we know this angle right here is 90 minus theta. So I'm going to say this angle is 90 degrees minus theta. Does everybody understand how I reached that conclusion? Anybody have any questions on that? This is going to happen over and over again, so I just want to make sure y'all are following me. Make sure you ask me questions if you don't, if you have them. Now, the other thing is this y axis, this negative y axis, and this positive x axis are perpendicular to each other, right? So that means this whole angle right here is 90, and it turns out that this angle plus this angle has to be 90 degrees. Okay? This angle is 90 minus theta. So I'm going to say 90 degrees minus theta plus this other angle, which I'll just call alpha, is equal to 90 degrees. I'm working out all the work here just to show you exactly what's going on. In the future, I won't take all this time to show you all of it, but I need to show it to you now. So I'm going to go ahead and solve for alpha. What we can see immediately is I can subtract 90 degrees from both sides. And of course, that's going to cancel out this 90 with this 90. And that's also going to cancel out this 90 with this 90. And in fact, what I'm going to get is alpha is equal to theta. So I can now say, no, that's not alpha in there. That angle is in fact theta. So now I can make a right triangle out of the weight, and that right triangle is going to be this vector and this vector. Remember, the way I do components is I go from the tail to the head, but I do so by going parallel to the x and y axes. So if I do the y axis first, it's going to be in the negative direction, followed by the x axis second in the positive direction. So that's really what my vectors are. So now I can represent this M, or excuse me, this mg, this weight, I can represent that by a red y component that is the y component of mg, and I can represent it by a green x component like that. And these two, of course, are at a right angle. And obviously, I drew it a little bit off, so I'm going to just stretch the head of the weight vector a little bit. Okay. Now you can see that I have a right triangle, and this green side, which is the x component, is going to be mg sine theta, and this red one, which is the y component, is going to be mg cosine theta. If you watch episode 1 of The Big Bang Theory, you'll hear them specifically say they're trying to push a box up the stairway, and they estimate the angle of the stairway is 30 degrees, and they say, okay, now we've reduced the force from mg to mg sine 30 degrees, call it one half. So now we've reduced the force that we need to push this TV up the stairs. We've reduced that by a factor of one half just by sliding it up the incline instead of having to lift it. So you can see that they're actually doing this specific problem. All right. So now I have this. Now I can write in the actual summation of the forces. So the summation of the forces in the y prime direction equals mass times acceleration in the y prime direction. Notice this incline, or this box on the incline, is just going to slide parallel to the x prime axis so that y is always going to be zero. It's going to be zero, and then you wait a split second, it's still going to be zero, and you wait a split second, it's still going to be zero. That means the y velocity is zero, and the y velocity is always zero, so the acceleration in the y direction is zero. So now what we have is in the positive y direction is f sub n, in the negative y direction is mg cosine theta, and all of that is equal to zero. So that tells us that the normal force is actually equal to mg cosine theta. So now we found yet another way we can alter the normal force. Sometimes when you're laying on a when you're something sitting on a perfectly horizontal surface, generally the normal force will be equal to the weight. But we saw when someone pushes down on the box, that increases the normal force. But if someone lifts up on the box, that decreases the normal force. Now here we have a tilted plane, and we automatically got that the force is no longer the weight. The normal force is now mg times cosine theta. Okay, so we did figure out part of it, which is what's the normal force on the box. That's part A. Now I'm going to use the summation of forces in the y direction, or in the x direction. Summation forces in the x prime direction equals mass times acceleration in the x prime direction. Now in this case, we are actually not saying the acceleration in the y direction is zero because it is going to accelerate down the incline, right? So we're going to leave it there, but it's the only acceleration, so I don't need to subscript it x. And in this case, I see there really is only one force parallel to the x-axis, and that's the mg sine theta. So this is going to become mg sine theta is equal to m times a, which clearly you can divide both sides by m, and you see that a is equal to g sine theta. And yeah, that turns out to be the fundamental formula if you want to calculate what the acceleration is on an incline of angle theta. the acceleration will be g times the sine of theta. That's what I was telling you when I said Galileo discovered that you couldn't study vertical motion very well because he didn't have good timepieces. So he decided to study things on inclined planes because he could relate the actual acceleration on the inclined plane to the vertical acceleration. And this is actually what he would have gotten is the vertical or the plane acceleration along the inclined plane is g times the sine of the angle. So if you just take A and find out what that is and then divide that by the sine of the angle, then you'll get the acceleration due to gravity. And that's how he discovered the acceleration of gravity is about 9.8 meters per second per second. So now I've gotten the equation for the normal force and I've gotten the equation for the acceleration, and it wants us to evaluate that for a specific case, specifically 10 kilograms at 30 degrees. So for part C, M equals 10, I'm going to call it 10.0 kilograms, and theta equals 30.0 degrees. A is equal to question mark. To do this, all I have to do is say, specifically because they want to evaluate for a mass and an incline, I'm assuming well, I'll say that they want to know acceleration and the normal force, just for the heck of it. So the normal force, Fn, is equal to mg cosine theta. Therefore, we get 10.0 kilograms times 9.80 meters per second per second. That's going to give me 98.0 times the cosine of 30.0 degrees, which is root 3 over 2. So I'm going to take 10 times 9.8 times cosine 30, and that's going to give me 84.87 newtons. We only had, even the way I made it up, we only had 3 sig figs. So that's what the normal force is for this particular case of C. And the acceleration, of course, is A is equal to g sine theta, which equals 9.80 meters per second times the sine, times the sine of 30.0 degrees. That's obviously 1/2. So that gives me 4.90 meters per second is equal to A, and that's our acceleration. Any questions on that? Now, one thing I should point out, I didn't do it last time. When I solved this problem right here, I didn't ever go back and figure out what the tension would be. Just show you really quickly how to find what the tension would be. Now that we know the acceleration or the angle theta with regards to the acceleration, we can actually figure out what t is. So for instance, from 2 prime, t is equal to mg over cosine theta. Okay, so that could help us a little bit. But what we need to do is realize that we have theta such that tangent theta is opposite over adjacent. So that would be a and that would be g, and therefore this would be a squared plus g squared. So the cosine of theta would be adjacent over hypotenuse. So that becomes mg over, now adjacent is the g, and hypotenuse is the square root of a squared plus g squared, like that. So we get that t, since the g's cancel out here, this g is going to cancel out with that g, and what we're going to get is that the tension in the rope is actually going to be m times the square root of a squared plus g squared. So that is a formula for the tension that you could in principle use. But I just wanted to finish that up just in case y'all hadn't thought about how you're going to go about solving for the tension in case they ask that. But I think that's a pretty good example. Anybody have any questions on that? All right. Well, we ended up finishing chapter four now, finally. It's just not quite as quickly as I thought it would be, but that's okay. I think it's really important that we have all these examples, so it's probably a really good thing that we went ahead over each individual example. I'm going to go into chapter five now. Just to give you a little bit of idea of what's coming, and I will finish it up next time. We're not going to be able to finish it today, but chapter five is using Newton's laws, colon, friction, circular motion, and drag forces. So what we're going to do is we're still, in fact, the rest of the semester, we're going to be using Newton's second law of motion various ways to solve physics problems. So all of this material is really Newton's second law. But in this case, we've got to examine the case of friction, the case of circular motion, and the case of drag forces specifically. We would like to be able to come back and say, okay, those problems we studied in chapter two of free fall where you drop a ball. What if we wanted to take into account the fact that air resistance is a real thing? That's what's going to help us do that. So, to do this, let's start off with chapter five. Chapter 5. That's called Using Newton's Laws and Friction, Circular Motion, and Drag Forces. Okay, that's what it's all about. Now, I'm going to stop sharing my iPad screen for a second because I want to use my video to show you an example that's very helpful. So, in order to make sense of friction, I need you to try something on your own. My calculator has these four little nipples on here, and actually two of them are missing. The little rubber nipples are missing. Those are good to have because they actually provide some friction forces. Whereas if it's just plastic, plastic against almost anything is very, very close to non-friction. It's like it has almost no friction. So really, it's best to have something with some friction. But what I would like you to do is consider like this calculator sitting on a tabletop. And if you give it just a slight push, it doesn't move. What's happened is that the friction force, and this is called static friction because the tabletop and the calculator are not moving with respect to each other. They're actually going the same speed as one way of looking at it, or just more specifically, they're not moving with respect to each other. Therefore, it's what we call static friction. If the if the calculator is sitting on the table and sliding this way or this way, then that's called kinetic friction. But the main thing is, I want you to imagine this sitting on the table and you give it a little push and you see it doesn't move. Then you try a little harder push and it still doesn't move. And you try a little harder, it still doesn't move, harder, it still doesn't move. And then all of a sudden, you'll get hard enough where it actually moves ever so slightly. But when it starts to move like that, you'll feel something very neat. Specifically, what you'll feel is it takes a pretty good size force to get it moving, but then it's like it releases itself and it's really easy to slide along. So what's happened there is you pushed harder and harder and harder until you reach the max strength of the static friction force. So static friction force is whatever the force needs to be to keep it from moving up to some maximum value. That maximum value is a formula given by F, the friction force, is equal to mu, the coefficient of static friction, times the normal force. That's the max the static friction can be. So when you reached that high force and then finally got it to break loose, you had reached the max friction force, the max static friction force. But immediately upon doing so, you felt that it was easier to keep it pushing because it turns out kinetic friction is weaker than static friction. So that is the whole premise that we need you to understand to make sense of friction. So with that in mind, let me go ahead and give you a graph of applied force versus friction force. So I'm going to draw a coordinate system, and this is F applied. So this is the force that you're applying, for instance, to the calculator. And this is the friction force. And I usually use that script F that you might recognize, for instance, from functions in algebra. So that's what I'm using. Now I'm going to go ahead and share my screen so you can see the iPad. I had forgot that, so I appreciate it, Michael, because I did almost forget completely. Now, what we saw when I was doing that little experiment was that when I pushed a little bit, the friction force would be exactly equal to how much I pushed. When I pushed a little harder, it would do it again. So basically, what we get here is a diagonal line that's exactly at 45 degrees. And the reason why it's at 45 degrees is because the friction force is never going to exceed the force that you apply to it, but eventually the force that you apply to it can exceed the friction force. So, for instance, if I apply a force of, let's say, 1.0 newtons, then this will go up and go over, and the friction force will be 1.0 newtons. If you apply a force of 2 newtons, then the friction force is going to meet that standard and say it's 2.0 newtons. And that's going to continue up until you get to this max value. And this is F static max. Notice I subscript it with an S to say it's static. And that is, in fact, equal to mu static times that normal force that we've been solving for in the previous problems. Okay, so that's the max. However, once you applied that max, then it's free to move. And in fact, you're only dealing with kinetic friction at that point. So what happens then is the force actually drops down. And let's say it drops down to here. And that's the force from there on out. And just to make sure you know what that is, I'm going to use a slightly different color so we can see what I'm talking about here. This is F kinetic, which is exactly equal to mu kinetic times the normal force. So that's actually how friction behaves. The way we write that is we say the static friction force is less than or equal to mu static times the normal force, and the kinetic friction F sub k is just equal to mu kinetic times the normal force. And as luck would have it, your book is kind enough, or your textbook author is kind enough to give you a table of coefficients of friction. So if you look in table 5.1 on page 118, you see that wood on wood has a coefficient of kinetic friction, mu k is equal to 0.2. It has a coefficient of static friction equal to 0.4. That's the norm, by the way. The kinetic friction being smaller than the static friction. In this case, it's twice as big. That's the norm. That's why when you're pushing the calculator, you have to use a larger and larger and larger force until it finally breaks loose. And then all of a sudden, you don't need nearly as much force to keep it moving because the friction kinetic is smaller than the friction static maximum. If you look at ice on ice, that coefficient of kinetic friction is 0.03, whereas the static one is zero point 0.1. Again, static's bigger. Metal on metal, it's 0.07 for kinetic, it's zero point 0.1 for static. Steel on steel is zero point 0.6 and zero point 0.7. Rubber on dry concrete is zero point 0.8 and zero point 0.8. In that case, there's no difference. Rubber on wet concrete, it's zero point 0.5 and zero point 0.7. So we're back to the kinetic being smaller than the static, and so on and so forth. It's got rubber on other solid surfaces. It's got Teflon on Teflon in air. It's got Teflon on steel in air, lubricated ball bearings, synovial joints, which is your human limbs, stuff like that. So it's got all those in there. Now, something else that's important, what we just learned is generally mu static is greater than mu kinetic. Okay. Now, that allows me to teach a big concept, and I'm running out of time anyway, so it's probably better for me to focus a little bit on concepts. I've taught a lot right here, just in terms of the friction forces and how they behave, but I want to show you something very important. So, for instance, when it snows every year, you get out your weatherman comes on TV and tells you, all right, everybody, the roads are slippery, and if you have to drive, which you shouldn't, you should stay home if you can at all. But if you do have to drive, you need to know how to drive on ice. And to drive on ice, you got to remember to turn into the skid. And they go through all sorts of things trying to explain to you what turning into the skid means. And I'll tell you that when you saw the movie Cars, if you did see the movie Cars, when they said you got to turn right to go left, and of course the character's like, duh, that sounds stupid. Well, he's actually right. That's really what's going on. So let me show you what I mean by that. First off, I've got to convince you that when you're driving your car, the friction force between your tire and the road is actually static friction. It's not kinetic friction. Even though the car is moving along, the way it works is the top part of the wheel is going. Let's say if your car is moving at 60 miles per hour, the top part of the tire is moving at 120 miles per hour that way relative to the road, and then as it goes around like this, it gets closer and closer to 60 downward. And then when it gets to the bottom, it's 60 backwards relative to the road, but the road is already going 60 backwards. So it's actually at the same speed. So let me show you what that means or how I can figure that out. So I'm going to go ahead and draw a wheel here. Okay. And let's imagine the car is actually going 60 miles per hour. So, with that in mind, that means the axle, with that in mind, that means the axle is going 60 miles per hour. And that's an important thing to remember. So, what I can say is if this is part of your car, then this part right here is going 60 miles per hour. That means the axle is going 60 miles per hour. But if you were to lift this car up on jacks like they do in a repair shop or whatever, and I wouldn't recommend doing this. You're not supposed to drive a car this fast. But if you have it up on the racks and then you push the accelerator until the speedometer reads 60, what you would discover is that the velocity of the bottom of the tire with respect to the ground, velocity of the tire with respect to the ground is actually in the negative direction, and it's going to be 60 miles per hour. The velocity of the middle of the tire, the axle, velocity of the axle with respect to the ground is actually going to be zero in this case because it's up in the air. But additionally, the velocity of the top with respect to the ground is going to be also 60 miles per hour. But in this case, it's positive. Okay. So if you want to calculate the velocity of the bottom of the tire with respect to the road, because this was when it was jacked up, then the velocity of the tire with respect to the road is the velocity of the tire with respect to the ground plus the velocity of the ground with respect to the road. Okay. In that case, you can see that you're going to get basically the velocity of the tire with respect to the ground is negative 60 miles per hour, and the velocity of the ground with respect to the road is positive 60 miles per hour. Therefore, you get the velocity of zero, and that shows you that the friction is static. So that's just a quick relative velocity calculation to show you that the tire basically comes to a stop for a split second when it's at the very bottom touching the road, so that the road and the tire are not moving with respect to each other. And that should make some sense because you know for a fact that when you spin out, that means the tire is moving at a different rate than the ground is going by under you. So when the ground is going by under you at the same rate, then it shouldn't spin out. So now that we have that, we can now say, consider a turn of a car like this. Okay. If we imagine our car going this way, that means these tires, I'm going to try to show that they're turning a little bit. So I'll put the tire just at a slight angle to allow it to make the turn. However, the back tires, assuming it's a normal car, are going to be going parallel to the road, which is straight ahead. Okay. So when you're riding around this curve and you hit a patch of ice, what is likely to happen is the rear end is going to spin out that way. So we're actually driving the car, by the way, and the car is going this way, and you can see that you got the front wheels turned a little bit. So as you hit the ice, normally the back end of your car is the lightest part, and therefore has the lowest normal force, and therefore has the least amount of friction on it. So the back end tends to spin out before the front end. Uh, when that happens, your car becomes in a position that looks a little bit more like this. And notice that is not parallel to the road in the sense that we're hoping. So it's already a done deal. The car is still going in this general direction, like the purple arrow was before, but that is obviously not parallel to the back tires, and the back tires therefore have kinetic friction instead of static friction, and we know kinetic friction is weaker. So that's a done deal. We've lost that, right? But they tell us to turn into the skid. So what it appears is happening, it appears that your car is spinning the back end to the left and your front end is trying to go to the right. So what you think you want to do is you want to turn your wheels in the same direction as the skid. Since your back end skidding around to the left, you want to turn your steering wheel to the left so that your tires will align parallel to the direction you're going. See how those tires are parallel to the green to the purple arrow? By doing that, what has happened is your back tires are still going to be sliding because you can't turn those. But your front tires now are aligned with the actual direction of travel, so they can recover static friction. Since tires parallel to path, we can recover static friction. And if you're too late, if you turn after it's too late so that your tires don't have the ability to turn far enough to align with the road, then you're just going to spin out and there's nothing you can do about it. But if you're quick enough to immediately feel your back end slipping to the left and turning your steering wheel to the left, then you're going to reestablish static friction, and that'll allow you to regain control of the car until the back tires line up and start riding in the same direction as the front tires are. And then you've got all four tires with static friction instead of kinetic friction. So that's the whole reason that you actually turn into the skid, is because static friction is larger than kinetic friction, and only when you turn your wheels to align to the direction of travel can you regain static friction. Does anybody hopefully feel a little better about understanding which direction to turn your wheel in the event of a skid? Hopefully that helps. I did actually one time I was teaching my former wife this. She had just gotten a Jeep and she had never driven in the snow before. And we were out in Western North Carolina area where it snowed on occasion. But she had just gotten a Jeep. She'd driven in the sand and raced boats and all that good stuff. And just she'd never driven in the snow. So she was a little nervous and she had to go across a couple bridges. So I explained all this to her. And I happened to be riding in a different car right behind her. And I watched as she went over the bridge and I saw the back end go like this, and then I saw the back end go like this, and I saw her what looked like she was turning properly, and then it goes like this, and then it went like this, and then next thing you know, I see her car spinning around like this, going across the bridge. Luckily, no cars were coming, so evidently I over explained it to her to the point where she didn't understand it all. So there is a danger of that, but hopefully I didn't do that to you guys. You all are free to go. I'll wait here till the last person leaves in case anybody has any questions. Don't forget about the online test dates are going to be moved, and I'll be posting an announcement and changing our syllabus about that. But there's a high probability that online test two will be due on Wednesday, a week from today. And then online test two might be a couple days there. Our test three might be a couple days thereafter, or maybe another 7 days later. I really want to fit in a couple of them before we do our next face-to-face test. You guys are free to go. Thanks for coming, and I'll wait for the last one to leave. Don't forget to chat me your first and last name if you haven't done so already. Thanks, Nathan.
Yeah, so I do have a question.
Yes, sir.
Because I have the textbook pulled up as well for static friction.
Mm-hmm.
F friction less than or equal to nu S Fn.
Mm-hmm.
Does that less than or equal to sign is the same thing that you have here, right?
Yeah, it's less than or equal to. That's what that diagonal line is, meaning that the friction force can be smaller than mu s times F normal. It's only going to do as much as it needs to match the force you're applying it to it, up until it gets to that max value, which is mu s times F normal. At that point, if you exceed that force, then the friction force gives away and you start dealing with kinetic friction.
Okay. And then the last question for VTR, that's referring to the axis or
Yeah,
GR, sorry, GR.
yeah. So that's the velocity of the ground with respect to the road,
Okay.
which was kind of weird. But the ground is going by basically at 60 miles per hour when you think of the car turning like this versus the road going by. That was it. And not only that, I was confident that I was losing people, so I sort of blew through it. There might be a little bit of. Probably should have used some different symbols because ground relative to the road makes no sense. If you look at one of my older videos, you'll see a better description of that part. The main thing is, can you convince yourself that at the bottom of the tire, there's no relative velocity of the bottom of the tire relative to the road? All of that was an attempt for me to show you mathematically using the relative velocity formulas to show you that the velocity of the bottom of the tire was exactly equal to the velocity that the road goes by, and therefore they're not moving with respect to each other.
Okay. So will they always be equal as far as like the VTG?
Yes, in this case, well,
Well, I guess not equal, but like derivative of each other.
Yeah, they're related in relative velocities such that remember the first suffix or the first subscript has to be equal to the first subscript here. The last subscript has to be equal to the last subscript here, and the middle two have to match each other. That's just the formula that I gave you guys for doing relative velocity, and it just makes the world a little easier to digest if you use that kind of principle.
Cool. Okay.
Okay. Yeah. So what I was shooting at was basically the idea that when you go 60 miles per hour, the tire is turning at 60 miles per hour. But when you go 60 miles per hour, the axle's moving at 60 miles per hour to the right. So if the bottom of the tire is moving at 60 miles per hour relative to the axle, then it's going negative 60 miles per hour relative to the axle, which happens to be the same as the velocity that the road is doing relative to the axle. So you get zero on that. It definitely would have been better if I said the velocity of the tire with respect to the axle and then the velocity of the tire with respect to the road.
I
Uh,
see.
but that would help out a little bit. And that's also where you get the idea that, check this out, the top of the tire is actually going like 120 miles per hour.
Mm.
So if you screw up, like if you've ever seen a tractor, they have those big tires right here, and the top of it's right next to a person. So
Yeah.
luckily they don't go very fast. They might go 20, 25 miles per hour. But if they're going 20 miles per hour, then that top is coming at you at 40. And therefore, if a rock shot out of the treads or something, it's going to fly out at 40 miles per hour, even though you're only going 20. So that's part of what happens when you see this math of the tire spinning at 60 means the bottom's going 60 this way, the top's going 60 that way for the axle sitting perfectly still. So when the axle all of a sudden is going at 60 miles per hour that way, then 60 miles per hour plus 60 miles per hour at the top gives you the 120, and 60 miles per hour to the right minus 60 miles per hour to the left gives you zero at the bottom.
Mm.
That's the relative velocity calculation I was trying to show you.
Okay. That's interesting.
Hopefully that helps a little bit better. I realized as soon as I did it that I was losing people, just because I wasn't getting the questions that I normally get. It's a little confusing, but anyways, the main thing is, as long as you know that clearly the tire is not moving with respect to the road at the bottom, unless you're spinning out, then you've got what you need.
Cool. Thank
All right,
you.
you're welcome.
Have a good one.
You too. See you, Michael. Parker, do you have anything?
Can you hear me now?
Yes, sir.
Okay. Um, I just had a few questions on like turning stuff in and like seeing
Okay.
my like I read the syllabus again today just to make
Hmm.
sure I had a bad feeling that I wasn't
Did you miss
turning.
something?
Yeah, and like because I was looking at the labs and like I turned the first two in when I was doing the third one,
Hmm.
printed out all the pages just to like make reading better.
Gotcha.
But where do the lab grades go?
Okay, they will pop up in the grade book, and
Mm-hmm.
you won't see them. You'll just see like a little box or a question mark or something like that in your grade until I grade them. I haven't started
Mm-hmm.
grading the labs. That's my goal this weekend is at least grade
Okay.
grade lab one. But I also got to finish test one. I had
Okay.
my last student take that today, so or
Oh,
late
okay.
last night. So hopefully I'll get the first. I'm going to do the test one, get those graded. Then I'm going to start doing lab one, and doing your homework on mastering automatically makes mastering put that grade into my grade book, so that'll appear
Mm-hmm.
too. I just have to update it every so often or put it on automatic update, and it'll keep track of it. Have you noticed your homework scores in the grade book?
Yeah, I've been seeing like the homework scores like automatically go in. So I
Good.
was like that's where I thought it was like, how come these are automatically going in? And then like these I was like, I gotta ask.
Yeah, the
So
non-automated stuff relies on this dude that's like a crazy lazy person, so it's just it's not getting done.
it's all good. It's okay. I was just making sure it wasn't like I wasn't doing something wrong.
No, no, yeah,
Um
that's your instructor doing something wrong.
okay, yeah, I'll make sure I get lab 3 and 4 and then today.
No problem. Like I said, long as if they're in before I go to grade them, I'm
Hmm.
not going to count them absent. I'm not required to do that by the syllabus, but that's what I do. So don't stress too much. If you feel like you're a little overwhelmed and you need a day or two before you start this next lab, then take a day or two. Best case scenario is I might grade labs one and two before Monday, but I can't imagine doing more than that.
Okay. Also, like I'm doing Calc 2, and that's like a lot for me right now.
Yeah, that's a
Uh,
lot during the summer.
for physics, there's also a lot of formulas. I've been like trying to read them and study them.
Hmm.
Do you have like a method to like kind of make them click?
I tell you, if you learn the process of deriving the kinematic equations, then they'll be stuck in your head forever. But the good news is you really don't have to because I give you the equation sheet. It's just a matter
Hmm.
of getting enough experience using them. Even if you don't derive them, you use them enough, you're always going to remember them.
Okay.
The other thing is, if you remember the dimensional analysis stuff we did in chapter one,
Hmm.
it's really easy to conjure up what the terms are like in the x equals 1 half at squared plus v0t plus x0 equation because there's no other way you can be it. If you're going to have an a term, you're going to have to get rid of those seconds squared. So that means the t has to be squared. You remember that came from an integral, so clearly it had to have a 1
Hmm.
half out in front of it. So 1 half at squared, you got that. The other one has to have initial velocity. Well, that's meters per second. So clearly I got to multiply that by a second to get meters. So that's V0t. And then clearly the last term is just the initial position. That has to have units of meters. So that's just X0. So all of that stuff going in my brain is what makes me memorize it, or at least be able to find my way back when I've forgotten it.
Okay.
Okay. So, and don't
Hmm.
worry too bad, especially during the summer. I make sure y'all have all your equations in the summer because it's a bit much to ask for all that
Hmm.
memorization in a 10 week.
Yeah. Hmm. But thank you for
No
that.
problem.
I
Let me know if
was,
there's anything
yeah.
else I can do to help you. And remember, you can always text me. That's the easiest way to get up with me in a reasonable amount of time. So let me know if I can do anything for you.
Okay. Thank you. Good night.
Thank you. Have a good one, Parker. All right. Thanks for coming, everybody. I think that went well. See ya.